In today's session, we will be discussing about some numerical examples on theory of simple bending. In last session, we have discussed about the theory of simple bending, which says that m by I equal to f by y equal to e by r. So this is the equation of simple bending based on assumptions. Based on some assumptions made, the equation for simple bending is derived as m by I equal to f by y equal to e by r. Okay, where m is the bending moment, I is the moment of inertia of the section of the beam, f is the stress at a distance y from neutral axis, e is Young's modulus, and r is the radius of curvature of the deformed shape, deflected shape. So this is bending equation. So based on this, we solve some numerical examples. So what we can do with this is, we can find the strength of the beam section, strength of the given beam section. What strength is? Bending strength. We can find bending strength of the given section. At the same time, we can also find the safe load that the beam can carry with maximum stress being known. When we know the maximum permissible stress, we can find the load that can be applied on the beam, the safe load that can be carried by the beam for the given maximum limiting stress. Okay, yeah. We'll proceed now with some examples. So first example reads like this: an I-section girder 200 mm wide and 300 mm deep with flange and web thickness 20 mm is used as a simply supported beam over a span of 7 meters. So here the span of the beam is 7 meters. Cross section of the beam is an I section with width 200 and depth 300 mm. The girder carries a distributed load of 5 kN per meter. So UDL over the span is 5 kN per meter, and a concentrated load of 20 kilonewtons at mid span. So it also carries a concentrated load of 20 kilonewtons at middle of the span. Determine the second moment of area of the cross section of the girder and the maximum stress that sets up in the cross section. Maximum stress set up in the cross section. And we know that maximum stress will be at the extreme fibers, either at bottommost or topmost fibers. Okay, sigma maximum, that we need to find. And we design the section for maximum bending moment. First thing, we design the section for maximum bending moment. And in this particular case of beam AB carrying UDL and central point load, the bending moment will be maximum at the mid span because of symmetry in loading. The bending moment will be maximum at the mid span. Okay, so for that bending moment, we calculate the sigma maximum. Okay, And the second moment of area means the moment of inertia. It depends on the cross section, shape of cross section, shape and size of cross section. Okay. Now you observe this figure. The total depth is 300 mm and width is 200 mm, which includes the flange thickness. Total depth includes flange thickness. Including flange thickness, the total depth is 300. So depth of web, if you consider web alone, if you consider the depth of web will be 260 because thickness of flange is 20 at bottom and top. Total depth is 300. So depth of web only, depth of web alone is 260 millimeters. Okay. So first part is to find the second moment of area, also called as moment of inertia. Okay, which can be calculated by the regular shapes, known values of moments of inertia of regular shapes. Okay, we can also use parallel axis theorem here by dividing this into three parts. Okay, top flange, bottom flange, and web portion. By finding out the moments of inertia of these three parts about the neutral axis separately. Okay, or we can consider the entire rectangle including this shaded portion. We can find the moment of inertia of this I section as moment of inertia of this entire rectangle minus moment of inertia of this shaded portion. Okay, that also gives the moment of inertia or second moment of area of the given section. This we have seen already, how to find moment of inertia for different sections, cross sections, and also the section modulus, which section modulus is I by y maximum, I by y maximum. Okay, it is clear. So the moment of inertia of this section, first we will find out the moment of inertia of the I section as the difference of the moments of inertia of a rectangle, that is a complete rectangle, enclosing this I section, and subtracting from that the moment of inertia of the shaded portion. That gives the moment of inertia of the I section. Okay, and this being symmetrical, we can directly find the moment of inertia about centroidal axis. First step is to position the centroidal axis. First, we need to locate the centroidal axis. Okay, but the section being symmetrical, we know that it lies at the mid height. The centroidal axis lies at mid height. Okay, we don't need to find it again because of symmetry. By symmetry, we can say that the neutral axis lies at the mid height. Okay, now from this, the moment of inertia of the rectangle enclosing this, for which the breadth is 200 and depth is 300. So BD cube by 12. BD cube by 12 means here B is, for moment of inertia of a rectangle, is BD cube by 12 about centroidal axis. Okay. Here capital B is 200, capital D is 300. Okay. So BD cube by 12 comes out to be 4.5. Here 200 into 400 cube by 12. So that comes out to be 4.5 into 10 power 8 in millimeter power 4. The units are millimeter power 4. And minus small b d cube by 12, where small b is width of the shaded portion, which is 200 minus web width, that is 20. What does that? What is that value? Is 180. 200 minus 20 web width. Okay, and d, small d is this height of shaded portion, which is 300 minus 2 times of flange thickness. Okay, so which is 260. So 180 minus 260 cube by 12. 180 minus 360 cube by 12. And this value comes out to be 2.64 into 10 power 8 mm power 4. So the moment of inertia for the given I section, given girder section, which is I section here, is difference of these two, that is 1.86 into 10 power 8 millimeter power 4. Okay, 1.86 into 10 power 8 millimeter power 4. This is moment of inertia or second moment of area. So this is the first part of the given example, given problem. Okay, and second part is to find the maximum stress which set up in the cross section. As we know, the maximum stress sets up at extreme fibers, either the top or bottommost layers. The topmost or bottommost layers. In this particular example, being symmetrical, the extreme fibers are at the same distance from the neutral layer. So the maximum stress will be the same at both bottommost and topmost fibers. These stresses will be equal because of symmetry. Okay, as we know that the stress is directly proportional to distance. For the given section, for the given beam means given cross section and given loading, m and I will be constant, so sigma will be proportional to y. Stress is proportional to the distance of the layer from the neutral axis. Okay, for the given beam and cross section, the stress at any fiber is proportional to the distance of the fiber from neutral axis. Okay, so the stress will be maximum at the extreme fibers. Extreme fibers means topmost or bottommost. In this case, because of symmetry, the distances of top and bottommost fibers will be the same, that is d by 2. Hence, sigma maximum will be same at topmost and bottommost fibers. The compressive stress and tensile stress, both are same. And that equation is given by the bending equation. Actually, this is a part of bending equation. M by I equal to sigma by y. F by y or sigma by f or sigma or f. We use the term sigma or f for stress. Okay, understand? So here sigma is given as m by I into y. M by I into y. Okay. So for sigma maximum, y is maximum. That is extreme fiber distance. Yeah. Now the maximum bending moment. First you need to find maximum bending moment. Where does it occur? Again, beam is symmetrically loaded. Okay. So the bending moment will be maximum at mid span. What is that maximum bending moment? Due to UDL, the bending moment is WL square by 8. Maximum bending moment occurs at the center, which is WL square by 8. And due to point load, maximum bending moment occurs again under the load, which is at the center. So maximum bending moment due to point load, concentrated load, is WL by 4 under the load. So this is WL square by 8. So due to combined loading, that is UDL and point load, this bending moment is WL square by 8 plus WL by 4 plus WL by 4. Okay. So here maximum bending moment is now given as WL square by 8, which comes out to be 35 into 10 cube. What is W in this case? Given loading. What is the given loading here? So given loading is UDL for 5 kilonewton per meter, and concentrated load is 20 kilonewtons. Okay, and span is 7 meters. Span is 7 meters. So WL square by 8 means 5 into 7 square by 8 plus W, capital W is point load 20 kilonewtons into L 7 by 4. Okay. This is in kilonewton meters. So it comes out to be 35 units are WL by 4. That is, this is 35 kilonewton millimeters. This is actually. Okay. In kilonewton meter, it is 35 plus, and this value is 30.63. 30.63. WL square by 8 is 30.63, and WL by 4 is 35 kilonewton meters. And here the value is kilonewton millimeters. 35 into 10 cube kilonewton millimeters. Okay. Yeah. This is kilonewton millimeters. Now, once you find maximum bending moment, substituting this value here in sigma maximum, which is given as M maximum into Y maximum by I. We know all the values. Sigma M maximum is the sum of this 65.63. This is in kilonewton millimeters, meters actually. Kilonewton meters into 10 power 6 Newton millimeters into Y maximum is half of this distance, that is 150 divided by I, moment of inertia. The value of moment of inertia what you have already calculated. So 1.86 into 10 power 8 mm power 4. So this is 1.86 into 10 power 8 mm power 4. Okay. So this value comes out in the units of Newton per mm square. Okay. Newton per mm square or mega Newton per meter square. Newton per mm square is same as mega Newton per meter square, because mega Newton means 10 power 6 newtons. Meter square is 10 power 6 mm square. So mega Newton per meter square or Newton per mm square, both are same. Okay. So maximum stress will be 51.8 Newton per mm square or mega Newton per meter square or megapascals. It is also called as megapascals. Pascal means Newton per meter square. You know that. Okay. Yes. So that's how we solve these problems of beams. Okay. Yeah. Now let us see one more example. A uniform T section is 100 mm wide and 150 mm deep with a flange thickness of 25 mm and web thickness of 12 mm. If the limiting bending stresses for the material of the beam are 80 meganewton per meter square in compression and 160 meganewton per meter square in tension, so the limiting values of maximum stress are different in tension and compression. Okay, in compression it is 80 meganewton per meter square and in tension it is 160 meganewton per mm square. Find the maximum UDL that the beam can carry over a simply supported span of 5 meters. So if the beam is simply supported over a span of 5 meters, over a span of 5 meters, what will be the load, maximum load that we can apply on the beam so that it satisfies these conditions? Maximum stress in compression 80 and tension 160. It is clear. So what load that we can apply on the beam? W, UDL we need to find, maximum UDL, intensity of load. Okay, yeah. For that, first we need to find, again by using the equation sigma maximum is equal to M maximum into Y maximum by I. Okay, first we need to find maximum bending moment. Okay, and we find the limiting value of load based on limiting stress in compression and limiting stress in tension. So least of these two loads will be taken as the minimum maximum load that can be applied over the beam. Okay. So before proceeding, first what we need to do is we need to locate centroidal axis, neutral axis, position of neutral axis. We need to find. Okay. After that, we find the moment of inertia or second moment of area of the given T section about the neutral axis. Okay, only after this we can find bending moment, maximum bending moment based on limiting stress in compression and limiting stress in tension. So how to find the location of neutral axis y bar from bottom 5? For that we use the expression y bar is equal to sigma a y by sigma a. Okay, or here we can uh, divide this area into two portions, the flange and web. Okay, so a1 means here the area of flange, y1 means distance of the centroid of the flange from bottom. This is y1. So ఇక్కడ y bar is a1 y1 plus a2 y2 by a1 plus a2. So what is a1? Area of flange, 100 into 25. Okay, so that is 200, 2500. So y bar is a1 into y1. What is y1 here? You can see total depth is 150 minus distance to the center of flange from top, 12.5. So it is 135, 137.5 plus A2. A2 means area of web. What is the depth of web here? 150 minus 25. That is 125 into 12 into centroidal distance, 125 by 2. That is into 62.5 divided by A1 2500 plus A2 125 into 12. 125 into 12 is how much it will be? 125 into 12, 1500. Okay. Yeah. This gives the distance of neutral axis above the base. Above the base. Okay. Which comes out to be 109.4 millimeters. The distance of neutral axis above the base is found to be 109.4, and from top it is 150 minus this, it is 41.6 millimeters. Okay. Now, knowing the location of centroid, we can find moment of inertia about the centroidal axis by using parallel axis theorem again. For that also we consider the areas 1 and 2 separately and use parallel axis theorem. Okay, and find the moment of inertia. Okay, that is the moment of inertia is moment of inertia of flange portion. What is the width of flange? Width of flange is 100 mm. Thickness of flange is 25 mm. Thickness of web is 12 mm and depth of web is 125 mm. Okay. Yeah. So here the moment of inertia of this about its centroidal axis, flange about its centroidal axis is BD cube by 12 plus area 2500 into h1 square. So moment of inertia about any axis is moment of inertia about centroidal axis plus AH square. This is parallel axis theorem. Okay. Moment of inertia of flange portion about its centroidal axis is BD cube by 12 plus AH square. Area into H is distance between the axes, and in this case it is H1 is 41.6 minus 12.5. Okay, that is 29.1 square plus for web portion base is 12 and depth is 125. So BD cube by 12, that is centroidal moment of inertia of this, which lies at a height of 62.5 from base. So what is the distance between these axes H2? We want the moment of inertia about neutral axis of the T section. So distance between centroidal axis of web and centroidal axis of the T section as a whole, H2, is 109.4 minus 62.5. So how much is it? 0.9. So 6. 46.9. 46.9 square. Sorry. Plus AH square. A is 125 into 12 into 46.9. This is area into h. H is this distance. So this value comes out to be 7.36 into 10 power minus 6 meter power 4. This is in millimeter power 4. We have to convert it into meter power 4. How to convert 1 meter power 4 is equal to 10 power 12 millimeter power 4. So this is the conversion part. Okay. So you have to convert millimeters into meters. So this is the moment of inertia value. Knowing this moment of inertia, next to find the maximum bending moment, based on compressive stress, based on limiting compressive stress, maximum compressive stress, which is given to be 80 meganewton per meter square or Newton per mm square. So sigma maximum in compression is 80 Newton per mm square. And moment of inertia value, just now we have calculated 7.36 into 10 power minus 6 meter power 4. You can convert this into millimeter power 4 only. That is 7.36 into 10 power 6 millimeter power 4, multiplying with 10 power 12. And Y maximum is in compression 40.6. Distance of maximum distance in compression zone is 40.6. Extreme fiber in compression is at a distance of 40.6 millimeters from neutral layer. So substituting these values, what are they? Sigma 80, I value 7.36 into 10 power 6, and Y 40.6. So this gives bending moment in Newton millimeters. Kilonewton meters lo convert చేసుకోవాలి into multiplied by 10 power minus 9 kilonewton meters, and it comes out to be 14.5 kilonewton meters. Okay, after converting you will get 14.5 kilonewton meters. So this maximum bending moment is based on maximum compressive stress. Similarly, we find maximum bending moment based on maximum tensile stress also. Maximum tensile stress. So what is that tensile stress? Yeah, maximum tensile, based on maximum tensile stress. So it comes out to be 10.76. Same. Sigma maximum in tension is 160 meganewton per meter square or Newton per mm square. I is same, and Y maximum. Y maximum is extreme fiber distance in tension. What is the extreme fiber distance in tension? 109.4. Just now we have calculated the distance of extreme fiber from neutral axis in compression tension zone. That is bottom zone, bottommost layer. This is nothing but the distance of bottommost layer, because in simply supported beam the tension zone means bottom of the beam, compression zone is the top of the beam. Okay, so the extreme fiber distance in tension is 109.4. that we will take here as Y maximum. sigma maximum is 160. Substituting these values, you will get the maximum bending moment as 10.76 kilonewton meters. Okay. Now, this is 14.5, this is 10.76. So, the allowable value is 10.76 only. Okay. Because if the bending moment exceeds 10.76, then the stress, maximum stress in tension zone exceeds the limiting value of 160. Okay. So, for this to be satisfied, the bending moment should be less than or equal to 10.76. So, we will take the maximum bending moment as 10.76 only. Okay. Now, with this maximum bending moment, for a simply supported beam with UDL, we know the expression for maximum bending moment as WL square by 8. So this value is 10.76. Substituting this here, we will get W as 8 into M maximum by L square. So 8 into 10.76 into 10 power 6, 10 power 9 Newton millimeters. We are converting it into, otherwise not necessary. Kilonewton meters only. And L is 5. L square is 25. So this gives the load W in kilonewton per meter. In kilonewton per meter. Okay? Yeah. Which comes out to be 3.4 kilonewton per meter. So this is the allowable load. Okay? This is the load that the beam can carry so that the given condition of stresses is satisfied. Okay, so that's how we'll find out.
Like, share and subscribe. Hit the bell icon for more updates.